All right, well, my name is Dan Swenson, and I am the chair of the Rocky Mountain section of the MAA. To everyone here, welcome, and thank you so much for joining us here today. I would like to take a moment to thank the organizers for this year's meeting. Even though this year's conference is virtual, we are hosted by the faculty of Metropolitan State University, Denver. Many thanks to MSU Denver for graciously putting this conference together, and thanks especially to our conference co-chairs, Dr. Mona Mokanasu and Dr. John Ethier, both of MSU Denver. I think it's safe to say that when MSU Denver volunteered to host a meeting, this was not exactly what they had in mind. They thought that they would be hosting us in person on their campus in downtown Denver, and they thought it would happen in 2020. Of course, things didn't quite work out that way, but suffice it to say that this event has been a long time coming, and I think it will be worth the wait. I would also like to thank our partners, Hawks Publishing, for once again sharing in the hosting duties and for taking care of so many technical details that make this conference possible. This is the second year in a row that we have partnered with Hawks to virtually host our meeting, and our contacts at Hawks, including Sydney, as well as Kelsey and Ryan. Thank you so much for being so responsive to all our requests and for all your hard work over the past weeks and months. It is truly appreciated. Thank you also to our section webpage editor, Oscar Levin. He has been fielding requests basically nonstop over the past however many weeks. Oscar, can you add this to the webpage? Can you post this? And he always comes back and says, sure, no problem, here you go. If you know Oscar, you probably are not surprised by that. So Oscar, thank you very much for your service. And to everyone who is here with us today, thank you for joining us. I hope to see you throughout this weekend. In particular, I hope to see you all at tomorrow's business meeting. However, since I know that not everyone will be able to attend that, and because we don't technically have a banquet this year, I wanted to make sure and publicly recognize two individuals. These are the winners of our section's 2 teaching awards. So the 2022 Early Career Teaching Award for Excellence in Teaching in the Mathematical Sciences goes to Dr. Michael McCuckey, Colorado School of Mines. He was nominated by Dr. Gregory Foschauer. We want to acknowledge all the hard work Dr. McCuckey puts into his teaching to influence many students and colleagues at Mines. He has worked on multiple course design projects, including revising the Calculus 1 course and examining the effectiveness of those changes. He's also coordinated classes, he's done postdoctoral and faculty mentoring, and co-founded a teaching seminar. The testimony from his peers and his co-creation and co-leading of the department professional learning community speak to his interest in improving teaching throughout the department. One former student and mentee captures Dr. McCuckey's passion for teaching by these words: Dr. McCuckey believed in me as a student and as a teacher. His excitement for teaching astounds and inspires me to teach others whenever I have the opportunity. His encouragement has helped me be confident to ask questions that go beyond the surface level of content in all of my classes, not just mathematics. So thank you, Dr. McCuckey. And the 2022 Burton W. Jones Award for Distinguished College University Teaching of Mathematics goes to Dr. Bob Cohen from Western Colorado University. He was nominated by Dr. Jeremy Muscat. We want to acknowledge all the hard work Dr. Cohen puts into his teaching to foster curiosity and to generate excitement about mathematics. His colleagues and former students praise his ability to infuse a deep excitement and love of mathematics into a wide range of courses he designs and teaches. He was recognized by his colleagues as the main reason for growth in the number of math majors and minors. He created an actuarial program, he organized Section Next activities, and he's been involved in undergraduate research in mathematics, among many other contributions. A colleague from another department, observing their students after Bob's courses, stated, Bob not only connects with the students, but he has been particularly effective at showing them how to apply math to their particular focus. So thank you, Dr. Cohen. Congratulations once more to both of our award winners for 2022, and thank you so much to our award committees for their hard work. I think this is really important work, and those committees always do an outstanding job of selecting outstanding recipients, as they have done again this year. And finally, to everyone who took the time to nominate someone thank you so much. We truly appreciate your time and effort as well. Well, that's enough out of me. It is now time to welcome our first plenary speaker for the 2022 section meeting. We are delighted to have with us today Dr. Jennifer Quinn, the president of the MAA. Really just thrilled to have her with us. We originally got in touch with Dr. Quinn when we thought we would have her at Black Hill State. That meeting will be next year, April 21st, 22nd, 2023. Mark your calendars. Well, a couple of twists and turns later, and now she's finally here with us. Jenny, thank you so much for your flexibility. If you don't know Jenny Quinn, I invite you to read her bio in the program. It is a truly impressive list of accomplishments, the prizes she has received, including the HIMO Award for Distinguished College or University Teaching, and also the Beckenbach Award for her book, Proofs That Really Count, The Art of Combinatorial Proof, which she co-authored with Arthur Benjamin. Plus, she is the president of the MAA. She is also a professor of math at the University of Washington, Tacoma. You might also know Dr. Quinn from her virtual social hours that she has hosted for MAA members, or maybe from her blog, Math in the Time of Corona, which I can personally vouch for. So if you're looking for some collected wisdom and some entertaining posts, please check that out. But don't do it right now because she is here with us. The title of her talk is Epic Math Battles, Counting versus Matching. So Rocky Mountain section, to kick off our 2022 meeting, please join me in welcoming Dr. Jennifer Quinn. Dr. Quinn.
Thank you so much. It is a real pleasure to be here, though I was sort of looking forward to being on an airplane and coming to Colorado. Initially, I was looking forward to coming to Black Hills, and then I was looking forward to coming to Colorado, but this will simply have to do. And I am always grateful to visit sections, see what everyone is doing that's unique and special in their own section. And I already believe that of the Rocky Mountain section. So I've seen lots of love going by in the comments, and it's just a wonderful thing to see. So this is meant to be a very interactive talk. And if we were in person, I would be hoping you would be making lots of noise and hooting and hollering and voting with your claps. But since this is not in person, we will be doing the talk instead using a Desmos work activity. And I am just going to put this here. You don't have to have a Desmos account. You can join the Desmos sheet at any time, and I will prompt you when you need to go there. But without further ado, I need you to suspend your disbelief, and we will begin our epic math battle. So let me share my screen with sound. All right, so here it comes. Epic math battles. Welcome, ladies and gentlemen, to this afternoon's epic math battle, where two mathematical techniques are going to vie for mathematical superiority. And you, as the observers, will get to decide who wins yourself. So I would like to introduce to you our speakers. The first contestant is someone who is beloved by many. She's familiar to everyone. She's known to use all her fingers and all her toes, and her favorite mathematical technique is to ask a counting question and answer it two different ways. I present to you, representing the mathematical technique of counting, the Countess. That's where you would be clapping out loud. All right. Her opponent is known to attack in pairs. He shows no fear of the negative sign. He uses his opponent's techniques to his own advantage, and his favorite mathematical technique is known as description, involution, and exception, otherwise known as mathematics to DIE, die for. I present to you, representing the technique of matching, Sir Match-a-Lot. Now, some of you may be new to this type of a combinatorial cage match, as it were. So let me explain the rules of engagement. There will be as many rounds as time allows. A mystery component is going to be revealed at each step, and the competitors are going to prepare their own signature identity featuring the required component and their respective mathematical technique of counting or matching. You, as the audience and experts, will get to judge the performance on whatever metric you deem fit, whether that metric is the complexity of the identity, the creativity of the identity, or the sheer elegance of the presentation. Round X yields the winner X points. And without further ado, let us reveal the first required component: the positive integers. Now, Sir Match-a-Lot and the Countess have been sent to soundproof booths to think and formulate their identities. So while they head off and just gather their thoughts, let's do a little bit of strategery and think about where they might be going. First of all, what is an identity? Identities can be trivial. 0 equals 0 is absolutely a valid identity. I don't know how pleased you would be if that was the identity they chose to present. Identities can be beautiful and useful. I'm sure many people in the audience today have used the particular identity sine squared of x plus cosine squared of x equals 1 more than once. Or identities can be truly mind-boggling. This particular one comes from the mind of Srinivasan Ramanujan, who, if you are not familiar with Ramanujan, he was a clerk from India who otherwise knew infinity. He saw patterns that the rest of the world is still struggling to understand at a time before computers. So just remember, Ramanujan's soul left this earth in 1820 at the age of 32. So it'll be interesting to see what kind of identities our competitors come up with compared to this range of identities that you're looking at today. I need to put this there. Okay. First, let's sort of pregame what kind of moves we can expect from each of our competitors. The Countess likes to use binomial coefficients, n choose k. So remember that n choose k counts the number of ways of picking a subset of size k from a set of n objects, n distinct objects. And just as a quick example, if you're not really familiar with them, 4 choose 2 is going to be equal to 6 because we have 4 objects. Let's just call them 1, 2, 3, 4. And we want to make subsets of size 2. So the subsets will be 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. There's 6 of them, so 4 choose 2 is 6. Now remember, these are subsets. that means that the set that contains 1 and 2 is the same as the set that contains 2 and 1. Order doesn't matter. So we'll expect to see lots of binomial coefficients from the Countess. Sir Matchalot, on the other hand, likes cancellation. And that's because when you take n and you add it to negative n, total annihilation. It gives 0. And that is how he matches things up. So we will expect cancellation, usually just canceling one thing at a time. All right, now that we know what to expect, we are very fortunate to have a hidden camera in the Countess's booth where we can be watching her work ahead of time. And as you can see, she's trying to come up with a physical representation for what an integer k could possibly count. Oh my, her first instinct, which is very natural, she's sort of crossed out. If you take the set of elements 1 through k, there are k ways to pick something out of it. But that's not going to give her the identity she's interested in. So let's see what she does next. Oh, so instead, she's picking pairs of integers where the largest element of the pair is k plus 1. And as she's writing right now, if the largest element is k plus 1, then the element that precedes it comes from that set 1 through k. So there will be k choices for the other element of the pair. So you can say that there will be k pairs where k plus 1 is the largest element of the pair. And yes, she's giving me the signal. She's ready to present. Sir Matchalot is ready. So let's call them out and have them present their dishes to you. She's going to express the sum of the first n plus 1 positive integers in a simple closed form. And here is her identity. Let me get a pointer. Here we go. So here is her identity. The sum of the integers 1 through n equals the binomial coefficient n plus 1, choose 2. So remember, what is her technique? It's to ask a question and answer it 2 different ways. So the question she's posing is how many pairs of distinct numbers can be chosen from the set of 1 to n plus 1? And the answer is, we're picking a subset of size 2 from n plus 1 elements, so certainly the answer is the binomial coefficient n plus 1, choose 2. But now, what's her second answer? She's counting the pairs based on the largest number in the pair. So calling the largest number k plus 1, we saw this in her movie, there are a total of k possible pairs. All right. So what does k plus 1 range between? The smallest the largest number can be is 2, because that smallest pair is going to be the pair 1, 2. So the largest number of that pair is 2, and the largest of the pairs can be the largest number we're allowed, which is k plus or n plus 1. So k plus 1, the largest number in the pair, ranges from 2 to n plus 1. That means the index k ranges from 1 to n. Each one of those results in k possible pairs. So for each largest element, we get summing over all possibilities, 1 when the largest element is 2, 2 when the largest element is 3, 3 when the largest element is 4, up to n when the largest element is n plus 1. So we have the sum of 1 to n, that's answer 1, has to be the same as answer 2, which gives us the equality of her identity. And the crowd goes wild. So, yes, I love the comment from Dominic. Sir Matchlot has his work cut out for him. Excellent. Let's see what he has to prepare for us. Drama. He's going to add drama with negative signs. All right, so here's the identity Sir Matchlot is going to present. And you notice he's still taking the integers, and he's looking at an alternating sum, adding a negative sign to every other term. And he's getting an answer, a nice closed form answer. So let's see where he brings us, how he explains this to us. Do you see that there is a commonality here? He too is looking at pairs of integers given a value of k between 1 and n. He is looking at pairs of integers, a k plus 1, where k plus 1 is the largest integer. There we have it. So very much the same thing as what the Countess looked like, added. So notice we're getting a little bit concrete example here. When k is 1, the pair is 1, 2. When k is 2, the largest element is 3. So the pairs are 1, 3, and 2, 3. When k is 3, the largest element is 4. There are 3 pairs. And furthermore, if we line up the colors, when k is 1, there's 1 of them. So this 1 in his sum matches to the 1 pair in the column corresponding to k equals 1. When k is 2, the yellow column or the golden column, there are 2 elements which match up with the negative 2 in his sum. When it's 3, there are 3 elements that are positive 3 in his sum. And when it's 4, it's negative 4. So the colors are telling us what's positive or negative. We understand what the representation of these elements is, but now we have to understand what's the matching. How is he matching things up? How is he matching up the positive 1 things to the negative 1 things? Because you and I know that 1 plus negative 1 equals 0. And then stuff goes away. All right, so what's the involution here? The match, involution is a fancy term for matching. All right, so notice he's taking any element A, B, and he's looking at whether the sum of the entries is odd or even. When the sum of the entries is odd, he adds 1 to the second component, to the largest component. When the sum of the entries is even, he adds negative 1 to the second component. Adds negative 1? Yeah, that's right. It's the same as subtracting 1, right? Okay, let's just see his matching for a second. So let's pick an example. Let's just pick 2, 3. 2 plus 3 is 5. That's odd. So the result should be we add 1 to the largest element. So it gets matched to 2, 4. 2 plus 4 is 6, which is even. So we would subtract 1, matching us back to 2, 3. All right, so it really is a true matching. Wonderful. And the negative 1 of the 2, 3 adds to the positive 1 of the 2, 4, giving us 0. And we only have to pay attention to the things that didn't get matched up. And where are they? They sit here in the final column. What didn't get matched up here? Let's take 2 plus 5 is 7. 7 is odd, so we should add one more. But that would push us out beyond the maximum we're allowed to have for our element in the pair. The largest we're allowed to have here for this example would be 5. So that's why 2, 5 has no partner. So for this small example, the only things we have to worry about is who doesn't get a match. And the people who don't get a match here are the things in the largest column that don't have enough elbow room to add 1. What are they? They're the pairs where A plus B is odd and B plus 1 is too big. Well, that's half of the things in this column. That's when K is even, half of the things work. What about when K is odd? So imagine the K equals 4 column isn't here at all and just focus on the K equals 3 column. There would only be one thing matched there and 2 unmatched. So it's going to be half, but we're going to have to take the ceiling of that because it's an integer. So we're going to take the ceiling, that's n over 2 with the ceiling, and then we have to make sure we put the right sign to it. When K, or in this is even, we end up with a negative entry. And when K was odd, we end up with a positive entry. Therefore, it's -1 to the K plus 1 times the ceiling of n divided by 2. So yes, and now what that means is it's your turn to vote. So once again, either you will vote for the Countess for the sum of the positive integers through n is the binomial coefficient n plus 1 choose 2, or you will vote for Sir Matchalot, who gives us the alternating sum, which is about half of n with the appropriate sign. Now to vote, you're going to have to go to Desmos. So if someone could throw the link back in case people didn't get it at the beginning, I am going to switch over to Desmos. I'm going to put it in teacher mode, and I am going to shoot it over to please vote for round 1. And at the moment, I have about 8 people online. Do you need the link? Do people need the link? I will put it in again, just in case. So that's the direct link as a student. And you should be able to go online and vote. I don't want you to be biased by someone else's decision. This is really your vote to make. So I want to let people have a moment to vote. Before I reveal the answer, let me look at, so we have 43 people in the Zoom meeting. About half of you have logged on to the Desmos sheet. I'm gonna give you a minute. Okay. So this is where I would normally be asking you to clap loudly and declare your approval. All right. Are you ready? I hear the roars through the screen saying, yes, I'm ready. Let's see the summary. We have a clear winner from the people who have participated so far. 17 votes for the Countess and only 9 votes for Sir Matchalot. Lovely. Many people have put in their answers, which is charming. I will look those over later, so thank you. So feel free to keep this up. Obviously, we'll come back and vote again later. So let's go to round 2, which means I do this. All right. Oh, here, let's celebrate. Okay, I have to not be in the laser pen to celebrate. The Countess wins round 1. All right, so let's go to round 2. One might think the Countess has an unfair advantage with binomial coefficients, but let's see what people come up with. This time, we're going to use the closed circuit feed above Sir Matchalot's desk. And what I love about Sir Matchalot is he's a little old school. He really loves his Haragumo chalk and working on a blackboard. So this is just a little reminder that binomial coefficients are the backbone. They are Pascal's triangle. The components there, indeed. This first entry he has here is 0, choose 0. The second line is 1, choose 0, and 1, choose 1. He's written out the triangle. We're seeing that if you take the alternating sum of things across the triangle, that you get 0. That's fabulous. So there's definitely an identity there for him to go work on. And let's see what they come up with. I don't expect anything different from him, an alternating sum of binomial coefficients. Well, perhaps he's going to surprise us here. Oh my, that's quite the identity. All right, so let me go back to my laser pointer. He's taking an alternating sum of a binomial coefficient, but it's not the binomial coefficient I was expecting. N is fixed, and K is the index that's changing there. And the answer is going to be either 1, 0, or -1, depending on the remainder mod 6. So that is not at all what I was expecting based on his previous work. All right, so let's see what he says. Given K, n minus K choose K counts tilings of 1 by n boards with K dominoes and n minus K squares. Okay, this might take a little bit to make sense out of. So you can imagine a square domino tiling, square dominoes. Okay, I can imagine that. And it's a tiling, okay, given K, counts tilings of a 1 by n board. So I have a board that's n cells long. It has K dominoes. So K dominoes cover 2K squares and n minus 2K squares. Okay, so 2K plus n minus 2K means it covers K squares. I'm on board. So it's definitely, if I have K dominoes, I understand that I'm covering a 1 by n board. All right, so that's what, and n minus K. So if I have n minus 2K squares and K dominoes, and I add those together, that gives me the total number of tiles. So there are n minus K tiles in this tiling of a 1 by n board. And if you know you have n minus K tiles and you pick where the dominoes go, everything else has to be squares. All right, so n minus K choose K is in fact tilings of an n board with K dominoes. Got it. Okay, the positive terms, the terms that are positive here, have an even number of dominoes. The terms that are negative here have an odd number of dominoes. Okay, so let's have a picture. So here's a tiling, a square domino tiling, and the involution is looking for the first instance when the tiling is breakable at a cell of the form 2j 3j plus 2. So that means it's breakable at j equals 0 would give me 2, breakable at 2, or breakable at 5. So breakable at 2, breakable at 5, breakable at 3j plus 2. 3j plus 2. Okay. Notice, imagine if you were breakable right here at 2. That means the first section of that would have to have been 2 squares or a domino. But if it's not breakable here, then there's a domino over cell 2 and 3, which means this had to be a square. So if the first instance of being breakable at something that is congruent to 2 mod 3, if this is the very first instance, then what came before it is entirely predetermined. It's got to go square domino, square domino, square domino, until right before the break, where it's either 2 squares or a domino. And that sets up the involution, because if you have a 2 squares, turn it to a domino. If you have a domino, turn it to 2 squares. It still has the first instance of the tiling of the form 3j plus 2 in the same place, but we change the number of dominoes by 1. One of them will have an even number of dominoes, and one of the pair will have an odd number of dominoes. So they will cancel each other out. That's fabulous. The exception is going to depend on the length of the tiling mod 6. If the tiling is congruent to 2 mod 3, either 2 or 5 mod 6, then that last tile is a break of the right form. So everything will have one of these first breaks, and everything gets matched up. So the outcome is everything cancels, 0. If, on the other hand, let's say we're in this form of 6m or 6m plus 1, okay, 6m or 6m plus 1, what that means is you have square domino, square domino, square domino, 2m times, and either you end or there's another square. So the outcome here is only one tiling doesn't get matched up. One tiling gets missed. And that one tiling, what sign does it have? It depends on whether it has an even number or an odd number of dominoes. And it's clear, because the exponent here is 2m, that it is an even number of dominoes. So it's got to have an outcome of +1. And finally, when we have 6m plus 3 or 6m plus 4, we have square domino, square domino, square domino, but this time it's going to happen an odd number of times and either end or have an extra sign. Again, there's only one thing that doesn't get matched up, and that one thing, because it has an odd number of dominoes, has an output of -1. So there we have it. We believe it. And now it is the Countess's turn. A double sum of binomial coefficients. Whew, okay. Wow, okay. So this is a double sum. I know how much my students love double sums. It's a very symmetric looking sum. So n is fixed, and it's n minus I choose j times n minus j choose I, where I and j are our summation indices. And the answer is a Fibonacci number. Well, I'll be darned. Whoa. Okay, so let's see what she's done. Question: how many square domino tilings of a board of length 2n plus 1 exist? Huh. 2n plus 1. She says it's a Fibonacci number. I think I need a little bit more convincing. What do you think? All right. So fk, little fk, is going to be the number of tilings in question. Okay, so fk is just going to represent how many there are. And a tiling of length 1 can only be done one way. Absolutely. A tiling of length 2 can be done two ways, square, square, or domino. A tiling of length 3 can be done three ways. Okay, so these look, I mean, we have a nice pattern happening here. 1, 2, 3, could be 4, could be 5. What is it that convinces us that these really are Fibonacci numbers? Well, let's look for the recurrence. A tiling ends either with a square or a domino. If it ends with a square, it has a tiling that's one less in front of it. That would be fn minus 1. And if it ends with a domino, it has a tiling of length 2 in front of it. That would be fn minus 2. So tilings satisfy the Fibonacci recurrence. And these are initial values in the Fibonacci recurrence. If we are so bold as to say there's one way to do nothing, then I absolutely agree that little f of k represents the number of tilings of length k, and it is a Fibonacci number. Now, if you belong to the Fibonacci Association, you might think, but I like my initial conditions to start at 0. And I do too sometimes. I absolutely do. Just not now when we're counting things. I like the index to match up with the length. Okay, here we go. Small side, small aside. Okay, so yes, I believe the answer is a Fibonacci number. So what about answer 2? Okay, consider the number of dominoes to either side of the median square. Okay, median square. This is an odd length tiling. So the number of dominoes has to be, no, that's wrong. Not the number of dominoes. The number of squares has to be odd. There's got to be at least one square. But then after that, there could be 3 or 5. There can't be an even number of squares. So having an odd number of squares means that there is one directly in the middle. That's your median square. So looking down here below, 1, 2, 3, 4, 5, 6, 7, there's 7 squares. There's 7 squares. And so this one that I put my laser pointer on, that's the median square, because then there are an equal number of squares on either side. There are 3 squares on either side. Okay, so we're going to consider the number of dominoes on either side of the median square. J is the number of dominoes to the left of the median square, and I is the number of dominoes to the right of the median square. It's just what it is. You pick an I and a J and we'll make it work. Okay, so now we have to think of, now we got to figure out what's really being counted here. All right, so how many squares are there total? How many squares are there total is the first question. Well, we started with 2n plus 1 cells. We had I dominoes, so we take away 2 I cells on one side, and we had j dominoes on the other side, so we take away 2 j cells. So this number, 2n plus 1 minus 2i minus 2j, is the total number of squares, which says that take the 1 away, divide by 2, n minus I choose j is the number on either side of the median square. Okay, so there are n minus I minus j squares on each side. On the left side, there are j dominoes and n minus I minus j squares. So add those two together for the total number of tiles. That tells you they're n minus I tiles, j of which are dominoes. So n minus I choose j is the number of ways to finish this tiling with j dominoes. And similarly to the right, there are n minus I minus j squares, but now there are I dominoes. So you get n minus j choose I tilings to the right. Multiply those two together to give you the total number of tilings and add them all up for all possible values of I and j that make sense. And once j gets to be too big, the binomial coefficient becomes 0. So it's okay having these sort of be infinite sums. We don't have to worry about making them pretty. And with that, the Countess has proven her identity. All right. You know what time it is now. It's time to vote for the winner. So let's go back to Desmos. Here we go. I will open up the next set of voting. This is for the round 2 winner. I'm going to not show you the votes while you vote for a minute. There are at least 4 people that need to move over and vote if you're still here with us. Does anyone need the link? Does anyone need more time? Of course you should vote. Okay, I'm going to reveal the votes. Ah! Whoa, okay, the Countess won again. All right. I do love median square. Median square is awesome. All right, so we are going to declare the Countess the winner for round 2, which means I go back to here and I declare the Countess as soon as I remove my laser pointer. The Countess is the winner of round 2. I am now watching my time, and I think I'm going to have to call it. I would love to show you round 3, but I promised it was only as time allowed. So with that, I think we know who the winner is. So let me go to here. The Countess won round 1. The Countess won round 2, which tells me for today, the winner is the Countess. I don't have applause here. All right. Okay, so let me just give you the highlights of today's match. There were only 2 techniques that were used today. The Countess always asked a question and answered it 2 different ways. And Sir Matchalot always did one of these description, involution, and exception arguments. If you want, in the literature, it's called a sign reversing involution. And I just don't think it's as well known as it should be. It's actually, personally, if I were voting, I would vote for Sir Matchalot. But you didn't hear me say that. And there's sort of a lesson here that where do these things come from? You know, there were lots of great comments happening. It's like, how do you come up with these things? It's really about understanding basic things deeply and figuring out where you can use the same argument and push your parameters until you come up with something beautiful and surprising. So it's really fun to set yourself up to try and take things that are well known, but put them in a context that really makes them concrete. My students will always hear me say, I hate induction. So many of these identities are things that are proved by induction, and I want to see them in a physical context every time. That is my preference. So if you want more, first I have to give credit to an incredible artist by the name of Greg Nemec. He did my avatars for me, and they are definitely worth looking at very closely. So he is a wonderful artist, and I am grateful for his work. If you want to see the third round, which I did not get to, which is also an awesome round, you can read about it in Math Horizons. You can get more details there. If you like these kinds of asking a question and answering it two different ways, the book I wrote with Art, Proofs That Really Count, that's pretty much all it does. And it starts with Fibonacci number, it generalizes, and it moves on from there. And the proof I didn't get to is talked about in this final identity. So with that, I'm going to thank you for your time and your wonderful comments. And I'm happy to answer questions, if there are questions. I'm going to stop the screen share. I'm perfectly happy to bring Dan back to tell people what to do next.
Yeah, I think, sorry, you put me on the spot here. Looks like the next, we do have, I think, about 9 minutes before the next sessions begin. There is a question in the chat here. So to everybody who's in the room, I think the next sessions begin at 2:05, and you can, should be links back from the platform page. But Dominic asked, what's the simplest identity you've ever seen a clever proof for? The simplest identity, clever proof.
Shoot. Okay, I am really bad at I'm really good at partial orderings, and like an absolute total ordering is really hard on me. It's like when someone asks, what's your favorite movie?
Well, is there one that you would rank highly in that list then?
I still have to think about it,
Okay.
but I'm glad I have a chance to say something. I have opened up the rest of the Desmos, and if you go to the last page, I actually have asked just an open-ended question. You can approach it anytime, which says, what's your favorite math identity? Because I'm always looking for new and interesting identities to present. I mean, I have an entire book of identities I love. I have an entire book of identities I love. It's like picking one of your children. I just can't do it.
All right. Understood. Well, thank you so much. Wonderful way to get our meeting started. Thank you so much. And thank you to our section visitor, Jenny Quinn, and thank you to everyone who attended. And as I say, the next sessions do start at, I think 2:05 is what it says in the schedule. So thank you so much, Jenny. Fantastic, pleasure being in the room for this.
My pleasure to be here. I'm going to save the chat because I always like to, so I can read what people wrote later and go figure out what to go see next.
All right, thank you. Yeah, see you.
All right, bye.